Yeah, could you confirm my voice is audible and screen is visible? Hello? Yeah, my voice is audible. Screen visible. Is my screen is visible? Okay, thank you. Now, so once again, good morning. Once again, good morning. So we are going to discuss about the principal component analysis. So this is used for dimensionality reduction. Internally, we are implementing dimensionality reduction. This is one of the compression technique. Okay, so one simple machine learning algorithm is, that means one of the simplest machine learning algorithm is principal component analysis. Sometimes we are calling it is PCA. This is used for dimensionality reduction purpose. So those definitions and other things we discussed yesterday. So using this compression algorithm, PCA compression algorithm, we are storing our points in a way that it requires less memory. Okay. By using that compression technique, sometimes we lose precision. That means accuracy, clarity. That we are missing. So to get better results, even after doing the compression, sometimes we need clarity of that information. For that, we are doing encoding and decoding techniques. Okay, so this is one of the optimal code which we are generating. So you know that optimal code is a better code. Okay, in terms of efficient memory utilization as well as the precision point. For that, we are using this optimal technique using optimal code point C. So this is a code point, optimal code point that we mentioned yesterday. Okay, so minimize the distance between input and its output recognition or reconstruction. So that means what is the use of this minimized distance between input X and its corresponding output value? So that means we are going to reduce the size, compression size. Okay, so with that we are finding the compression data. One second. Okay, the compression we are doing. So for that we need we are using L2 loss function. That is also we defined what is L1 loss function, L2 loss function, L3 loss function, and functions related information yesterday. Okay, and now we are deriving the theorem. Say for example, we have a function f of x. What is this f of x? F of x is a function. Okay, f of x is equals to c. So what is this function? This is optimization code. We are generating optimization code by applying the input value x with function. Okay, that this function is a mathematical function. Okay, by applying this function, we are generating optimal code. This is our target during the encoding. This is encoding process. In encoding, we are applying this function. So and in the decoding function, okay, the destination side we are using decoding function to decode this encoded object. Okay, that will generate the output. Okay, that will generate the output finally. This value is approximately derived from the function output function g. Okay, this output function is having the input as the encode value f of x. Okay, so this is output decoding function. This is input encoding function. So for this decoding function, we are giving the parameter as a encoding function because this encode function is having optimal code. So using that optimal code, we are applying some function. Using that function will generate output value x. So whatever the value given as an input, finally we are generating the output that is stored inside the x. That after doing some decomposition technique by applying some decomposition function. So for that, we are going to start our derivation with the decoding function. Okay, we are going to start with the decoding function. This decode function we can select by our choice. Decoding function we can select by our own choice. Say for example, I'm going to consider decoding function like g of c. So what is g of c? G of c is nothing but g of f of x, because f of x equal to c. We are replacing c value f of x. So we'll get g of f of x. Okay, so this g of c, I'm going to consider like a decoding function. Okay, this function is having one decode parameter. Okay, this is matrix. I'm going to consider as a matrix, and the optimal code. Okay, so, this is a decode function definition. We are designing or defining function like this. Okay, so this here D is a decode matrix or a decode parameter which defines decodes logic. Okay, so in our PCA, this decode value is a matrix. As I told you, this decode parameter is a matrix. This matrix is having orthogonal values. Okay, so these orthogonal values are construct each other with all columns as D unit norm. So how it is constructing the column values of this orthogonal matrix means in terms of unit matrix, that is unit norm. By using unit norm, we are constructing this, we are considering this matrix value, orthogonal matrix value. This is used for measuring the distance using this norm function. So we are measuring the distance using norm function, so that we are applying norm of D. These basic definitions we have studied in the last class. Gone through once the material and recollect the information. Then we are applying L2 lossy function. Okay, because obviously after applying these methods, encoding and decoding methods, we'll get like there is a chance to lose some precision. So for that reason, we are applying lossy function, L2 lossy function. So what is L2 lossy function for this optimal code C? This is a minimum value. Okay, this is a minimum value. Okay, minimum value of our x, input value x, and the decoded function g of c. Okay, decoded function g of c, and we are applying L2 norm, right? So you have to consider norm square. Okay, so this value is, it is retrieved from the minimum value of these columns. The minimum value of these columns will be considered as a norm square. So this minimum value is in terms of augment. So you need to call this is ERG min. ERG min in terms of optimal code C. So out of available all orthogonal column values, it considered the argument value. That argument value will have set of argument values. Out of all these argument values, we'll consider, we'll select or we'll pick minimum value because we are reducing the dimension. So usually there is a difference min and argument. Min is considered the minimum value of entire set, entire vector. Okay, so but augment min value is considered with particular parameter related. Okay, so it is considered only optimal code minimal value. Okay, for that we are using augmin x minus g of c. So this is a decoding function, and we are applying orthogonal unit function, norm function, that is square function. Okay, then we'll see. Here we would like to consider this term as A. You just see this. You need to concentrate from here because it is little tricky. It is having more mathematical calculations from here. You just observe carefully. So now we are going to consider this as a matrix A. So I'm going to define one matrix property A into A transpose. Okay, A into A transpose equal to A. And also sometimes we can call this is A transpose into A equal to A. Okay, so that means instead of taking this A, sometimes we can multiply matrix A with its transpose, or transpose of the matrix multiplies with normal self matrix, it generates self matrix again. Okay, so this is a technique we are using. So instead of taking a single matrix value, so I'm going to consider this representation because we are assuming this as A. Okay, so A transpose into A, either A into A transpose. You can take any one of. So now I'm going to take x minus g of c norm. Okay, g of c. So we are doing transposition of this matrix. Okay, it is not a norm function. We are taking a normal matrix with transpose, and you can multiply without transpose of a matrix. So it don't change. It doesn't change anything. The meaning is not at all be changed because A transpose into A equal to A. So like this we are making, and then we'll simplify this equation. So after simplification, we'll get like x transpose minus g of c transpose. Okay, into this is transpose is applied. Okay, when we apply transpose, we'll get the values like this, and x minus g of c as it is. You try to understand this concept. It is having more mathematical calculations. It is difficult to understand. Please concentrate. So this is the function here. So then we'll multiply this x transpose with this xp. So then we'll get like x transpose into x minus x transpose into g of c. Okay, this is completed. Now we are multiplying minus g of c transpose with this one. So what we have, minus as it is symbol, g of c transpose. Okay, g of c transpose into g of c into g of c. Then we'll multiply this with this. Okay, g of c and x is there. Okay, so total 4 terms we need to get, 1, 2, 3 terms. So now I am going to get minus x into minus. So I'm going to consider minus x into G of C transpose. Okay, so after that, you need to derive a measure equation. Again, simplify this. Again, simplify this by using distributive law. Again, simplify this. I'm writing next line. X transpose into X minus. So I'm moving on next page. So what we got? X transpose into X minus, sorry. Yeah. You just see here, X transpose into X minus X transpose into G of X minus X terms first. X transpose into G of X. This is X is multiplied with matrix A, and we are multiplying this G transpose with X and GC. GC, that means X into GC transpose minus GC transpose into GC. That we are going to derive. GC transpose into X minus. So what is this minus? Minus into minus plus. Okay. So you have to consider minus into minus is a plus. GC transpose into GC. This is after multiplying this value. So we are getting. So then by using distributive law, we can apply like G transpose, X transpose into X minus, see here, X transpose, okay, X transpose GC. And here also you can consider GC, X transpose and GC. So by applying distributive law between these two, that means I'm converting this as X transpose G of X. X transpose, it is simply replacing the dimensions like that. So what is this? A transpose into B, B transpose into A, like that. So X transpose into G of C. What is this? This is like A transpose B equal to B transpose A. Both are equal. So because this is one of the distributive law. So matrix multiplication allows distributive law, associative law, it's not allows the commutative law. Okay, you just remember those laws. So I'm redefining the laws. A plus B plus C equal to, we can write A plus B plus C. This is possible. Okay. And A of BC equal to AB of C. This is also possible. But AB is not equal to BA. This is commutative. So this is not satisfied. AB is not equal to BA, but A transpose of B equal to B transpose A. This is possible. This is commutative law. So this thing we are applying. So in place of B transpose A, I'm writing A transpose B. So this is this one. Then plus GC transpose and GC. GC, this is as it is. So now we'll consider these two things are same, minus 2x transpose of G of C. Okay, all these things are G of C only, not X, G of C. Okay. We have this term as it is, X transpose X. Last term as it is, GC transpose of G of C. GC transpose G of C. If I have a blackboard, I can write very clearly, try to this. Okay, so this is we got. So now we are changing this function into the minimal value. We need to consider argument. So by omitting the first term, okay, we are not considering the first term because we are performing argument. Okay, you just remember why we are getting this. So we are taking minimum value of the argument C. So wherever we have term C, we consider only that particular step. Otherwise, the remaining who is not having C, we won't consider. So this is X transpose X, we are not considering here. Here we have GC term, here we have GC term. So we'll consider these two. Okay, so optimal code. So this is optimal code C star equal to ARG min minus 2x transpose of G minus 2x transpose of G plus GC transpose and G of C. This is finally we got argument of C. So because it is having only arguments, minimum arguments, so those arguments terms which will be having C. So this is my decoding function. So this is my decoding function. For this we are applying vector calculation. For this min argument, we are applying vector calculations because we are doing optimization. As of now, we have derived only this value, but it is not an optimal value. So now we are doing optimization. For that, we are using vector calculus. So vector calculus is applied del C in terms of C vectors of minus 2x transpose minus 2x transpose. We are applying this for 2x transpose G of C transpose into GC. So for this we are applying in place of function G of C. In place of function G of C, I am using decoding matrix D and C. What is this decoding matrix C? Why we are writing DC? Because so this is GC. Okay, 2x transpose we are considering as it is 2x transpose, and in place of G of C we are using DC. Why we are using DC? So because G of C is DC. This is my first equation. Okay, this is my first equation. Wherever we are having G of C, we are replacing with DC. Okay, so in this equation, we are replacing this with DC, and also we are replacing this with DC. Okay, like that we are applying. DC plus DC plus C transpose into D transpose into DC. We'll apply this one. Okay. So why this C transpose, D transpose, DC? Because so we are applying GC transpose. What is GC transpose? GC is nothing but DC. DC whole transpose equal to C transpose and D transpose. This is a basic. Okay, so in place of that GC whole transpose, we applied C transpose, D transpose, and G of C as it is DC we are replaced. Then D transpose into D, it will become D, and C transpose into C, it will become C. So now it is DC, it will become DC. So this will become the DC. Okay, so now it is 2x transpose of DC, 2x transpose of DC plus instead of taking DC, so I'm going to consider C transpose into C. D is equal to C. Okay, so we'll consider only this because we are applying normalization vector, and also we'll take one term as common term, that is C. So 2C that equal to 0. This is equal to 0. Vector calculus. So now we can consider C value. C equal to D transpose of X. Why we are getting D transpose of X means whatever the terms which is having left side will multiply, will goes into the downside of this one. Okay, so down 1 by 2 X transpose and C. Okay, so denominator thing will consider with minus value. So we'll consider, right, C equal to D transpose of X. So this is a function, our function f of X. We are replacing C value with f of X. So f of X equal to C, right? So we can consider f of X equal to D transpose of X. Okay, means D transpose of X. This G transpose is decoding matrix. Okay. So this is the major thing which we are doing in decoding function. The similar way we are applying encoding. Okay, so similar way we are applying encoding using L2 function. It is very difficult. Using L2 function, we have applying decoding of the value in terms of decoding with the distance value, that is square root of xj, xj into decoding factor, decoding parameter into x of j. Okay, decoding factor using L2 function, d star equal to, we'll do like this. So then we'll get argument matrix X transpose. So this is about PCA. It's very difficult to understand. I'll give you material. The same thing is there. Just we are derived all these things. Simply we'll get encoding value and decoding value of the compression of our data element. Okay. So with this, I'm stopping today's session. If anyone having any doubts, please raise your doubts.